welcome to Mathmania Academy. In this video, we are going to discuss the Part C questions of December 2016. In the first question, it is given that A is a n by n non-singular matrix with real entries. Okay, by this non-singular, what do we mean by it? Like A inverse exists. So this is the primary information that is given. Okay, and B is a matrix which is the transpose of A. Okay, then with which we'll have to examine which of the following are positive definite. Okay, in order to examine the positive definite, as if we go with the definition, then we'll have to write down the quadratic form and see for all non-zero vectors in Rn we are getting that value is positive or not. That is by definition. And the other way is, if we have a real symmetric matrix, then we have some shortcut ideologies through which we can check the positive definiteness. Okay, basically let us see what is this A plus B, which is A plus A transpose, right? And here see what is A plus B whole transpose, that is A plus A transpose the whole transpose is nothing but A transpose plus A transpose the transpose, which is nothing but A itself. It is A transpose plus A. Matrix addition is commutative, so it is A plus A transpose. Therefore, what we get is A plus A transpose is symmetric. Okay, we have this matrix is symmetric, and let us see whether this is a positive definite or not. In order to get positive definiteness, what should we have? We must have all the eigenvalues are positive, right? Let me choose. I suspect this may not be true, so let me try to construct a matrix. Simply let me try to construct a 2 by 2 matrix. Okay, 1 0 0 minus 1. My A transpose would be what? My A transpose would be 1 0 0 minus 1 only, the same thing. When I add these two things, my A plus B would be what? 2 0 0 minus 2. Of course, this is satisfying all the requirements. It is a non-singular matrix with real entry. I am able to identify A transpose. When I add, I am getting another symmetric matrix. But this is not positive definite. Since it has two eigenvalues, one is positive and the other one is negative. Hence, it is not positive definite. For the same thing, identify the inverse of A. It is 1 upon determinant, that is minus 1. And this would be 1 minus 1 0 0 1, and finally we end up with the same matrix. Okay, if you know, then what would be B inverse? It is also 1 0 0 minus 1. Through the same argument we are able to establish that this is also not positive definite. Then we have AB. Okay, so AB, that is nothing but A transpose. Am I right? So here I can take the transpose and see whether these things are happening in a proper way or not. Okay, if needed, let me try it out. What is A B transpose? That is B transpose A transpose. Am I right? It is A transpose the whole transpose and A transpose. It is again A transpose. So the matrix AB is also symmetric one. Okay, let me find out the quadratic form associated with this matrix. That is X transpose A transpose X. So this may be written as A transpose X the whole transpose product with A transpose X. A is an n by n non-singular matrix. Okay, basically it is an n by n matrix. When I multiply that with the vector in Rn, I would end up in a vector, another vector in Rn. So this is basically positive since A transpose X is non-zero for X not equal to 0. Why so? Because A is a non-singular matrix and hence A transpose is also a non-singular matrix. This is happening to be true for all x non-zero in Rn. Therefore, AB is a positive definite. Okay. 4. If it is simply AB, I am able to check it is a positive definite or not. Here we have ABA. I suspect this may not be positive definite. So, for which let me just take the same example. Okay, the thing that I have here. Okay, what is AB? AB is simply identity matrix. Am I right? Then from this ABA is what? It is 1 0 0 minus 1. From this it is clear that this is not positive definite. Okay. Moving to the next question, it says that we have again an n by n matrix such that each entry is an integer. So we have a matrix where all the entries are integer entries. And we have determinant, the product AB is identity with some square matrix B. Okay, so if this is so, given that AB is identity matrix, therefore this B is nothing but the inverse of A, right? They have not spoken about the entries of B here. Have that in mind. For a square matrix C, determinant of C denotes its determinant. Okay, that is the usual notation that we follow, and we'll have to examine which of the following are true. Okay, we have AB is equal to I. Therefore, determinant of AB is determinant of I, which is nothing but, since both A and B are square matrices, this shall be written as determinant of A into determinant of B, which is equal to 1. Okay. From this, if I deduce what is determinant of B, that is nothing but 1 upon determinant of A. If my determinant of A is 1, then determinant of B is 1. Option 1 is true. Right? A sufficient condition for each entry in the matrix B is an integer. Is the determinant of A is an integer? Is it so? Not necessarily, right? So, in option 2, what they are trying to say is determinant of A is some element in Z, some integer. Okay, let us say determinant of A is some x. Then what would be my B? It is 1 upon x times of adjoint of A. Since A is a matrix with integer entries, adjoint of A is a matrix with integer entries. But I'll have to divide each entry by x. Hence, it need not be a integer one. Okay. Hence, option 2 is false. B is always an integer matrix. No, not necessarily. Okay. Option 4 tells that a necessary condition for each BI, that is to be an integer. That is, B is also a matrix with integer entries. That can happen when determinant of A falls in these two categories. Okay. If B is to have integer entries, then this determinant of A must be either 1 or minus 1. Why? We have this thing, right? Determinant of A multiplied with determinant of B equals 1. Okay, we know that determinant of A is an integer value, and we expect this determinant of B to be an integer value. This is possible only when determinant of A is either 1 or minus 1. That is what option 4 says. Okay. Moving to the next question. Here we have a matrix 1 1 1 1 1 0, and alpha n and beta n are the eigenvalues of A to the rise n. Okay. First of all, let us recall, if lambda is an eigenvalue of A, then lambda to the power n is an eigenvalue of a to the power n. Okay, here if you find out the characteristic equation of a, that is 1 minus lambda, sorry, 1 minus x multiplied with minus x minus 1, which is nothing but minus x plus x square minus 1, that is x square minus x minus 1 equals 0, from which what we get is x is 1 plus or minus 1 plus 4 upon 5, sorry, 1 plus 4 upon 2, it is 1 plus or minus under root 5 upon 2. Okay, here your alpha 1 is 1 plus under root 5 upon 2 and beta 1 is 1 minus under root 5 upon 2. Why I have chosen 1 plus under root 5 upon 2 as alpha 1? Because they have given that alpha n, absolute of alpha n, has to be bigger than or equals absolute of beta n. That is why I have chosen this quantity to be my alpha 1. So from this, what is my alpha n? It is 1 plus under root 5 upon 2 whole power n, and beta n is 1 minus under root 5 upon 2 whole power n. Fine. If you look at these values, what is under root of 5? It is slightly bigger than 2. Am I right? It is 2 point something, so it is slightly bigger than 2. So 1 minus under root 5 is what? Smaller than 1 minus 2 upon 2, which is minus 0.5. Okay, which is smaller than minus 0.5. Okay, and this is a positive one, like it is one, it will be greater than 1 point something. Alpha n would be greater than what? Here if you just see, it is greater than 1 plus 2 upon 2, it is greater than 1.5. Okay, so it is 1.5 to the power n, and this is beta n is smaller than minus 0.5 to the power n. We have these two things. And when you make your limit go to infinity, that is when you make your n go to infinity, this is bigger than infinity. This is what you are getting. Infinity itself is large, hence it is bigger than infinity, which means alpha n go to infinity as n approaches to infinity. Okay, here limit n approaches infinity, beta n is what? Since 0.5 is a quantity which is smaller than 1, and when your n approaches infinity, this will shrink and we would get this is 0. That is, beta n approaches 0 as n approaches infinity. Okay, and from this it is very clear that whenever your n is even, okay, your beta n would be a negative quantity whenever your n is odd, and is positive whenever your n is even. So from this, if you just see, all the 4 options are true. Okay, moving to the next question. Here we have the vector space of all n by n real matrices. In that set, which of the following are linear subspaces? So we'll basically have to check which of the following are subspaces or not. First, in 1, what I have is collection of non-singular matrices. Okay, I'll have to check whether that is a subspace or not. Okay, if it is so, collection of non-singular matrices, right? We'll have to, if, let me choose whatsoever the vector space. Okay, here let me choose 2 matrices from V1. Okay, which tells me that determinant of A is non-zero and determinant of B is non-zero. I will have to check alpha A plus beta B. Determinant of this is to check. Determinant of this quantity is also not equal to 0 for all alpha and beta in R. I suspect this is false. So let me try to construct an example. Let me choose A to be an identity matrix and B to be minus times of identity. clearly determinant of A is non-zero, which is 1, and determinant of B is also non-zero. It may be either 1 or minus 1 based on the order of a matrix. Okay, and I choose alpha and beta to be equal to 1, then what happens? My A plus B, alpha A plus beta B is simply A plus B, that is 0 matrix. Okay, which has the determinant 0, so it is not a subspace. Okay, so the second, we'll have to deal with the matrices whose determinant is 0, right? So here, why I have chosen determinant thing? This A inverse and B inverse exist. If it has to exist, then the determinant is non-zero. That is why I have played with determinants. Here, they have said that determinant of A is 0 and determinant of B is 0. Okay, I suspect this is also not a subspace. So let me try to construct some examples. Alpha is 1 0 0 0. Okay, I should get the determinant to be equal to 0. That is why I am choosing this way. Okay, then what is my alpha A plus beta B? It is alpha 0 0 beta. Okay, and if I look for my determinant of alpha A plus beta B, which is nothing but alpha B, I'll have to prove for all alpha beta in R this is equal to 0, but that cannot be true. Only when either alpha is 0 or beta is 0 or both 0, I get this to be equal to 0. Hence, this V2 is also not a linear subspace. Coming to the third option, I get alpha and beta are in V3, trace of A is 0 and trace of B is also 0. Okay, now I have to find the trace of this one. If it is 0, then I am done. Since trace is a linear operator, this trace of alpha A plus trace of beta B. This is alpha times of trace of A plus beta times of trace of B. This is alpha times of 0 plus beta times of 0, which is 0. Yes, of course, this is a subspace. Moving to the fourth one, where matrix B is fixed. Okay, first of all, let me take two matrices X and Y from V4. Then what happens? My X can be written as BA and this Y can be written as BC, where B is fixed one. Okay, then I'll have to check alpha X plus beta Y. If I can write this as a multiple of the matrix B. This is alpha times of BA plus beta times of BC. Since this alpha and beta are scalars, I can play with it anyway. So this is B alpha A plus B beta C. So let me take this B outside, alpha A plus beta C. Right? The A which is multiplied with B should be a matrix from Mn. Since A is a matrix from Mn and C is a matrix from Mn, this linear combination is also a matrix from Mn. So this tells us that alpha X plus beta Y is a member of V4 and hence it is a subspace. Moving to the next question, here we are given that P and Q are invertible matrices. Okay, fine, good. Such that this condition holds. So with which we will have to examine the trace of this one. Okay. Since P and Q are invertible matrices, P inverse and Q inverse exists. So if you multiply P inverse to it, P inverse PQ is nothing but P inverse minus QP, and this is Q equal to minus times of P inverse Q P, or you may simply have P inverse minus Q P. So this means what? Q and minus Q are similar. This is what we infer from this. If it is so, trace of Q is same as that of trace of minus Q, and since Q trace is a linear operator, we shall take this minus outside. This is what we get. So from this what we get, trace of Q is 0. Here you have multiplied with P inverse, right? Instead, if you multiply with Q inverse, what happens? PQ Q inverse equals minus Q P Q inverse. Okay, here we would have P equals uh, okay, you just take this P to this side, then you would have what? QP Q inverse. So here what we get, P and minus P are similar. Okay, so using the similar argument, you can very well prove trace of P is also 0. Okay, this is the first option claims trace of P and trace of Q is 0. So examining the other options, trace of P is same as that of minus trace of Q. That also to the next True. Question. Here it is given that n is an odd number which is bigger than or equal to 7, and A is given to be a n by n square matrix with I plus 1. That entry is 1 for all I running from 1 to n minus 1, and this A n1, this entry is 1. Okay, let us see what can be this matrix A. So these are the diagonal questions. In diagonal questions, I have not specified anything, that except these entries, every entry is 0. So in diagonal, we will have 0 completely, right? And I comma I plus 1. If I start with 1, A1 2, this entry is 1. Then A2 3, that entry is 1 1 1. So this is what we have, and in the last row we will have 1 in the first position, and rest entries are 0. This is what the information given to us. So while writing down this matrix itself, you might have noticed that columns are changed in an identity matrix. Am I right? So, and it has only 1 and 0. So this can be, this is a permutation matrix. Okay, so if you write down the permutation cycle, what happens? Your first entry, if you do some transformations, or if you just permute it, when by suitable permutation, you must be able to identify a identity matrix, for which what should you do? The first column whatsoever is there in the matrix has to be placed as an nth column. That nth column has to be placed in n minus 1th position, and whatsoever is there in that position has to be placed in n minus 2th position. If we proceed this way, this is what we are going to get. Am I right? What is the length of this cycle? It is n. Do we have any other cycle? No. In a like it is an n by n matrix. In n cycle, the entire n cycle is in the, like, all the columns are covered in the this cycle of length n itself. If we have a permutation matrix, then the characteristic polynomial of such matrices are given by product of x to the power length of cycles, okay, minus 1. So this is the characteristic polynomial of permutation matrix. Here we have only one cycle of length n. So characteristic polynomial of this matrix is nothing but x to the power n minus 1. So this can be written as x minus 1 into 1 plus x squared till x to the power n minus 1. Okay, now let us examine the options. Option 1 claims that A has 1 as an eigenvalue. Yes, it is true. And option 2 claims A has minus 1 as an eigenvalue. Is that true? Not necessarily. If n value is lesser, like if n value is 2, then it may be possible. But for it is clearly given that n is an odd number. N is an odd number which is bigger than or equal to 7. So clearly it is specified that it has to be an odd number. If it is an even number, you can take x square minus 1 as a common term and you'll have the rest of the things. That then minus 1 can be an eigenvalue. Since clearly odd number that is specified, that is why minus 1 cannot be an eigenvalue. Okay, and A has at least one eigenvalue with multiplicity bigger than or equal to. Not necessarily, because this gives unique roots. Okay, this will have n minus 1 distinct roots. And A has no real eigenvalues. No, we have 1 as an eigenvalue. No matter whether we are getting any eigenvalue from the remaining part, but 1 is a real eigenvalue that is there for any matrix of this kind. Okay, so option 4 is also false. Moving to the next question. Here we have 3 distinct subspaces of R10 and each with dimension 9. So dimension of W1 is 9, dimension of W2 is 9, and dimension of W3 is also 9, and it is clearly specified that these are 3 distinct subspaces. So if you make the distinct, by distinct you could have understand that thing, and we are defining W to be the intersection of all these 3, then what can we conclude about it? Okay, dimension of any subspace Wj is dimension of R10 minus number of linear independent restrictions. Since it is given that 9 is the dimension, it is 10 minus 1. So only one linearly independent restriction is imposed. When you make W, that is W1 intersection W2 intersection W3, it will have 3 linearly independent restrictions. Okay, so dimension of W is 10 minus 3, that is going to be 7. So option 3 and 2 is are the right options. Okay, this is one way. Okay, and the other way of claiming it is, we have a result that maximum of 0 comma dimension of W1 plus dimension of W2 minus dimension of V smaller than or equals dimension of W1 intersection W2, which is smaller than or equals minimum of dimension of W1 comma dimension of W2. Okay, so here what is happening? 0, dimension of W1 is 9, W2 is 9, and it is 10, right? Smaller than or equals dimension of W1 intersection W2, which is smaller than or equals dimension of minimum of 9 comma 9. So this tells that 8 dimension of W1 intersection W2 is lying between these two things, 8 and 9. Okay, now we shall apply this again to what? The 3 things. 0 dimension of W1 intersection W2 plus dimension of W3 minus dimension of V. It is dimension of W1 intersection W2 intersection W3 and minimum of dimension of W1 intersection W2 comma dimension of W3. Okay, here we will have two possibilities. This leads to either dimension of W1 intersection W2 is 8 or 9. Here we have not made use the 3 distinct subspaces. That idea we have not made use here. We are just proceeding. If it is 8, what happens? It is 0 comma 8 plus 9 minus 10. Maximum of these two quantities is smaller than or equals the required dimension is minimum of 8 comma 9. This is what we are going to have, right? So this tells us that it is going to lie between 7 and 8. Okay, if we choose the other way, like if we choose this dimension to be equal to 9, so in that case what we are going to have, we would have 8 here, right? 8, and here also we'll have minimum of that thing. So dimension of w1 intersection w2 intersection w3 is less than or equals 9. So this is what, from these two things we'll have to claim. Okay, this is dimension of w, right? So 7 less than or equals dimension of w less than or equals 8, and it is again it says that 8 less than or equals dimension of w less than or equals 9. So from this we are able to see that dimension is bigger than or equals 7 and dimension is smaller than or equals 8. Here, why did we neglect it? Just because the linear restriction, that if you include that thing, three distinct subspaces, so if you include that thing, you will not have this option. Dimension of w1 intersection w2 is 9. This is possible only when w1 is contained in w2 or w2 is contained in w1, but that is not the case. It is clearly said that they are distinct. So this cannot be possible. That is why we have not consider what I have written here in green color. Okay. Moving to the next question. Okay. Final. Actually, we forgot to check the option now. That claims that W may not be a subspace. Okay, but that is not true because intersection of finite number of any finite number of subspaces is a subspace. Okay, so that cannot be true. Moving to the last question of this year, what is given is A is a real symmetric matrix. Then what can we conclude? Okay, A does not have 0 as an eigenvalue. Is it so? Choose 0, A to be the 0 matrix. It is a real symmetric matrix, but it has only 0 as an eigenvalue. Done. All eigenvalues of A are real. Is that so? Okay, let us check. Okay, let lambda be an eigenvalue of A. Then what can we say? Ax equals lambda x. Okay, I just take conjugate transpose to this. Then what happens? Ax whole theta, excuse me, is lambda x whole theta, which is nothing but x theta a theta is x lambda bar x theta, since lambda is a scalar. Okay, so this is what we have, and this is nothing but x theta. Since A is a real symmetric, we would be back to this A itself, and lambda bar x theta. Okay, just multiply with x on both the sides. What is this? This is lambda x, right? So x theta lambda x equals lambda bar x theta x. So lambda times of x theta x equals lambda bar x theta x, and this would give us lambda minus lambda bar x theta x equals 0. So clearly this x theta x cannot be equal to 0. Therefore lambda minus lambda bar should be equal to 0, which claims that lambda is lambda bar. Hence all the eigenvalues of A are real. Okay. No matter what real symmetric matrix that you are considering, all eigenvalues of that is real. Okay. Option 3 claims that if A inverse exists, then A inverse is real and symmetric. Claiming A inverse is real is not a big deal. Okay, you just apply A inverse formula, that is 1 upon determinant of A and adjoint of A. We are done. But now we'll have to prove it is symmetric. Okay, in order to prove A inverse is symmetric, what should we do? We have to prove A inverse whole transpose is same as that of A inverse. This is what we should prove, right? Let us consider this one. Okay, take a transpose. So A transpose, sorry, A inverse whole transpose is equal to identity transpose, which is nothing but identity itself, and this is A inverse transpose, and A transpose equals identity. What is A transpose? It is A itself. Am I right? Since A is a symmetric matrix. So here what we are going to get is A inverse transpose is A transpose, and hence option 3 is true. Option 4 claims that A has at least one positive eigenvalue. Who said so? Consider A is equal to minus times of identity. You are done. All the eigenvalues are negative. It is a real symmetric. That's it. So that's it about the questions from December 2016. Until I meet you in the next video, this is Suraj signing off. Thank you.